that. Thank you. Thank you for letting me know. All right. So once again, it is probably a better idea to use the operating system specific Discord client to watch the live stream um, from Discord instead of from YouTube, because YouTube has a horrible lag. So that means, when I ask a question and I wait like 3 or 4 seconds for people to ask questions and then I move on. For people who are watching the YouTube stream, by the time you hear my "do you have a question," it's going to be 19 seconds after in real time I actually ask the question. So there'll be a horrible delay between that. Um, so and the web interface does not do the live stream either in Discord. I'm not sure whether that is the problem. Hmm. Okay. All right. So continuing on with the demonstration, and I hope Murtaza can figure out how to get the live stream to work in Discord, because that really is a whole lot more interactive compared to using the web client for Discord. Okay, so moving on. K0 is just K0. I made a tunnel for K02, just so that we can use it over here, just so that things can look nice. Okay. And then we have the K1, K2, and K3 circuits. Each one looks kind of like this. Yesterday I worked on K2, which is this one, and the way I worked on K3 and K1 is I just copied and pasted the entire thing. I got rid of the getting, or the stuff that is in between. Change the AND gates and also the OR gate just a little bit. K3 is a little bit messy, but it's not too horrible. Okay, it is still just reasonable. I think YouTube should be streaming now. Yeah, YouTube is actually streaming. So I'm not sure why Julian says there's no YouTube. YouTube should be working. I can double check it. I just clicked on the link that was pinned. That is pinned at the top of Discord. YouTube should be streaming now. It is working. You can hear myself. Is actually streaming. Right. There we go. Okay. All right. Cool. So anyway, I worked on K1, K2, and K3, and we can see how all three, they make use of the 3-bit P, the 3-bit J, and also the 1-bit K0. This is why we can kind of connect everything kind of nicely, because P, which is a 3-bit tunnel, is now just multi-dropped into K1, K2, and K3. The same for G and K0, except K0 is a 1-bit thing. So that's how we interconnect P, G, and K0 into K1, K2, and K3. And the way we compute the sum is we have to go through an exclusive OR between the Q and also the K's. Now the tricky part is which 3 of the 4 K bits should be used to merge in order to feed into the exclusive OR. Some people initially use K1, K2, and K3, and that is not going to work, because if you use K1, K2, and K3, then we'll end up using K3 exclusive OR with Q2 to compute S2, and that is not correct, because S2 depends only on K2 and Q2. So you have to make sure that we connect K0, K1, and K2 to the merger in order to feed it into the multi-bit exclusive OR. K3 is on its own, its own output, because that is the overall carry of the entire addition. So that's kind of the overall design of the carry look ahead adder. Are there any questions about this lab, about the carry look ahead adder. Okay, all right, Sakio is typing. I gotta wait a little bit here. All right. Yeah, if you don't use the tunnels, that's fine, because you can just connect the output of these gates directly to the input of the K1, K2, and K3 circuits. So that's actually okay. The tunnels make the whole thing look a little bit nicer, and it's also kind of self-documenting. So otherwise, it's you don't have to use the tunnels. So as I said, the tunnel is for kind of self-documentation, because without the tunnels and you connect this wire directly to the inputs of K1, K2, and K3, then it's not as visual and it's not as documented of what we are connecting to K2 and K2 and K1, K2, and K3 subcircuits. So the tunnels are really useful for documentation. But it's also useful when you have a super complex design. Well, I wouldn't say super complex, but a slightly more complex design. So let me show you the processor itself. It is a little bit ahead of time, but I do want to show you that one, because this way you start to understand why we have tunnels. So let me go back to the processor folder. And this is the one. All right, so this is the actual processor that we'll be starting to use about mid-semester. And you can see how this is really kind of all over the place. So if I don't use tunnels like this, okay, and give proper names to the tunnel, you can kind of imagine that this design would be, it would just have wires flying all over the place, and it would be kind of difficult to track down, okay, which wire is connected from where to where. And that's why the tunnels come in handy, because they have their own names. And now at this point, to us, these names do not make sense, right? R uppercase O 0 EN is register output 0 enable. Okay, that's the shorthand of that. But by the time we get to this design, it will start to make sense. Okay, so the key is we need tunnels in order to make a design more readable. Now, comparing this to what we're dealing with, now obviously with this one, there's actually no particular need to use the tunnels, but I still want to connect the concepts, right? Because I still want to connect the concept of the G bits, the P bits, and the Q bits. So using the tunnels make those concepts a little bit more visual, compared to, oh, okay, it's in the notes we refer to those terms, but in the design, where are those terms? Those terms are here in the design. So I hope this helps to people to understand what the P, G, and Q terms are in the discussion, in the notes, in the modules. If it does, it's great. If not, well, I'll try to figure out something else to make it more visual. So are there any other additional questions about the carry look ahead design? Okay, I'm not seeing any questions. Okay, so if there are no questions, then we'll move ahead and talk about binary number comparison. Okay, and there was one comment somebody sent me, I cannot remember whom now, that there might be a correction that I need to do a little bit later. So I'll keep an eye out for that. All right, so let's get started on this particular module, because that's what today's lab is about. The prerequisite of this module is 283, which is binary addition, as well as 284, which is binary subtraction. So what we want to do is to say there are 6 different types of comparison operators that we are familiar with that C and C++ both support. So now the question is, how many are actually needed? Well, as it turns out, we just need one of them. Okay, of all of these, we just need less than. Now you can say, well, what about greater than? Yes, you can have greater than too. So because they are basically flip sides of each other. But in this discussion, I'll just say that what if there's a weird programming language where the only comparison supported is less than? Can we still implement all the logic, all the comparison that we need to when all you're given with is just less than? So this particular part here illustrates why we just need less than. X is less than y if and only if x is less than y. So that's pretty obvious, okay? Less than can implement less than. Great. What about greater than? X is greater than y if and only if y is less than x. So we just converted the greater than into a less than by flipping the operands, by flipping the expression on the two sides of the operator. So that's pretty easy too. So now we start to get into something a little bit more complex. Is what if I want to express x is less than or equal to y? Well, x is less than or equal to y if and only if it is not the case that y is less than x. Okay, to some people this is really obvious, and to some other people it is less obvious. So you might need to digest this a little bit if it does not seem intuitive to you. The next one is just flipping x and y, because x is greater than or equal to y is really saying the same thing as x is not less than y. Okay, so we got 4 of them now. The fifth one is x does not equal to y. X does not equal to y if and only if x is less than y or y is less than x. Okay, so are we still doing okay so far with these 5 comparison operators? Okay. Now, once again, I'm using the plus sign in place of an or. There was a comment from, I guess, yesterday that this is confusing. Well, it is a notation that I have kind of talked about. So the more we use it, the less confusing it would seem. So to people who think that this is really confusing, all I can suggest is to read it out. Okay, when you read an expression like this, try to reason out whether this is actually addition or whether it is a disjunction or. And 2 is to read it out. I mean, just kind of really just verbally read it out. So that will help people to understand or to remember that we use the plus sign to represent disjunction, to represent or. All right, so moving on to the last one. The last one is, how do we express x equals to y when all we have are the Boolean operators and or not, and just one single comparison operator, which is less than. So what we'll do is we'll take the not equal to, which is this part here, and put it inside a big negation. So this negation is negating the entire disjunction. So if something is not equal to, then it is equal to. So that's kind of the reason behind this one here. So that means, okay, this means in C and C++, there really is no need to give you all 6 comparison operators. The programming language could have just given you less than, and that's already sufficient to represent all of the other comparisons. So combining this, okay, combining this observation that less than is enough to implement all of the other comparison operators, as well as the fact that we know how to use NAND, NAND, negated AND, to implement all of the other Boolean operators. So this means if we really want to have a reduced feature programming language, all we really need is NAND as a Boolean operator, and less than as a comparison operator. Now, would you want to program in that particular language? Probably not, because things will look kind of really ugly, because things get blown up quite a bit. But in theory, it is already sufficient. So I just want to point out that is sufficient already. Now, the discussion of why we only want to deal with less than in this case has to do with the idea of CISC versus RISC. CISC, C-I-S-C, stands for Complex Instruction Set Computer, and RISC stands for Reduced Instruction Set Computer. In other words, in the CISC type of computer, they will give you all 6 comparison operators, okay? Not quite in the form of operators, but they will give you a very convenient feature so that it is easy to translate the 6 comparison operators into assembly language code. But in the RISC architecture, they may give you just 1 or 2 of the 6. And so you have to kind of only use those 2 to implement the same logic. So we'll talk about the trade-off between RISC and CISC at a later time, but I do want to point out that we want to boil everything down to just less than because of that. Because in the end, we just want to implement a RISC type architecture instead of a CISC type architecture. Moving on to section 3. So section 3 talks about how do we compare unsigned values. Okay, in other words, how do we compare the value represented by a bit pattern that should be interpreted in the unsigned fashion. So the first thing we need to do is what is the actual value represented by a bit pattern. So I'm skipping over all the way to here, and it might be useful to kind of go through the notation just a little bit here. So xi with the subscript I is indicating the ith bit of x or bit I of x, and we count from 0, and likewise for y. So with that in mind, we want to look at this little theorem here. And the actual proof of the theorem is not going to be important, but we just want to know the theorem. The theorem is saying 2 to the power of n is greater than the summation of I going from 0 to n minus 1, and then each term we are summing in this case is 2 to the power of I. So if I want to use an example, okay, let me pull my notepad down here. There we go. So if I want to use an example, for instance, we can say 2 to the power of 3 is greater than 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0. Now, can we keep going? Okay, can we say plus 2 to the power of -1 plus 2 to the power of -2 and so on? The answer is actually yes. Okay, but we are not taking this portion here because we are dealing with unsigned integers, so we are not dealing with the fractional part, and we are only concerned about this part here. So when you look at this, you say 2 to the power of 3 is 8. This is 4, this is 2, this is 1. And so we can now say 8 is greater than 7 is actually true. Okay, great. So why do we need this particular theorem? Okay, well, we kind of need it later on. Okay, so we are not, I'm not going to say why we need it, but by the time we get there, we'll be clear why we need it. So this portion here, okay, this entire portion is the proof of the theorem, which is this little statement over here. Am I going to ask you to prove a theorem by proof by induction in this class? The answer is no. If you have taken CISP310, you might want to give this a try, okay, just to make sure that you understand proof by induction, because in CISP310, proof by induction is one of the topics. If you're going to take CISP310 and you have time to read this portion, you might find it useful because this gives you a preview of proof by induction that you will learn in CISP310. So that's up to you whether to read that section or not. All right. So now we want to look at X, which is a bit pattern, Y is also a bit pattern, and each one has M explicit bits, okay? Because we can always say there's an infinite number of bits to the left-hand side and they're all zeros, right? So let's not deal with it. We just say that there are M explicit bits that are represented here. And we make the assumption that xi is the same as yi, and it is 0 for I is greater than or equal to m. That is actually, so somebody pointed out this and asked, did I mean to say I is less than m? And the answer is no. I did mean that I is greater than or equal to m. So if you plug in this portion into the value represented by an unsigned 8-bit number, all this is saying is I'm not going to deal with all the implicit zeros to the left of the bit pattern. That's all it's saying. Is that okay? All right. Looks like we are not getting any questions. Oh, okay, good, thank you. All right, so now we move on. And this notation is actually not needed yet at all, so you can kind of ignore that particular notation. So now we are saying that let's assume xi equals to yi for all the I index I that is greater than p this time. Okay, it's not m, it is some value p. So when we get down to p, okay, so when we look at bit p of x and bit p of y, then we can have several scenarios. The first scenario is when xp is 0 and yp is 1. Now remember, xi and yi are identical for all the indexes I that is greater than p. So this is the quote-unquote first bit that is different. If you're moving from left to right, okay, this is the first bit that is different between x and y. So at this time, I can already conclude that x is less than y. I don't need to look at the other bits. I can already conclude that x as a bit pattern is representing an unsigned value that is less than the unsigned value that y is representing. And it has to do with the theorem that we have already proved earlier, which is this part here. Because in this case, if yp is a 1 but xp is a 0, even if all the bits to the right hand side of p of x are 1s and all the bits to the right hand side of bit p of y are 0s, even if that were the case, okay, x is still less than y, and that has to do with the theorem. And then Martin has a question. What does bit p represent? So p is representing a bit position that we are concerned about. So we keep moving p from m minus 1 and hopefully all the way down to 0, okay, at some point, because we are basically just moving p one place to the right hand side in the binary bit pattern so that we can see if we can conclude whether x is less than y or not. Is that working? So this is how we move p. So how do we know, Catherine is asking, how do we know we are reading from left when using p? It has to do with how p is initialized and also how we basically perform the loop. Index I is kind of a local variable. So I is really just, so this use of I is only local to this particular statement. I does not transcend from one statement to the next. P is more persistent. P is basically an index for the entire discussion from all the way from here down to here. But the use of I is really just local, where it is just doing something like this. Is that okay? All right, cool. And I can give you a pictorial picture a little bit later. So moving on to the next line, okay, what if x does equals to 0 and y, okay, xp equals to 0 and yp equals to 1 is false. Then we move on to the next one and we test again. Now if xp is 1 and yp is a 0, then we can conclude that x is less than y is false. And somebody's going to say, but Tech, we know something even better. We also know that x is greater than y. But remember, we are only concerned about whether x is less than y. So all we have to say is x is less than y is false. Now, x may equal to y, x may be greater than y, but I really don't need to differentiate between those two cases because my only concern is whether x is less than y. All right, so what if these two conditions are both false? If both of these conditions are false, then we ask the question, is p 0 at this point? Because if p is 0 at this point, that means we have just compared every single digit in x and y, and everything turns out to be exactly the same. Then in that case, we also make a conclusion that x is less than y is false, because in this case, x equals to y. But the only conclusion I need to draw here is that x is less than y is false. I don't need to know whether x and y equal or whether x is greater than y. So what if they're all false? In other words, we look at this condition, it is false. We look at this condition, it is false. We look at this condition, it is also false. Then we go back to the first step, which is this part here. But we decrement I so that p we decrement p so that p is now 1 less than what it was. But then we go through this process again. And you can see this is basically just a loop to go through every single bit from bit 0 to bit m minus 1. No, the other way around. From m minus 1 down to 0. We compare one bit at a time, and when we see a bit being different between x and y, then we can immediately draw a conclusion. If not, we just keep going down to the next p, which is 1 less than the current one, and we keep doing it until p gets down to 0. Then if x and y are still, if we still cannot determine because the bits are all the same between x and y, then x is less than y is false. Because when you have an m bit number, you only have bit 0 to bit m minus 1. And that's also why we make the assumption that all the bits that are all the bits corresponding to positions that are greater than or equal to m are the same, because bit m is already out of the representation already. So with an 8-bit number, we only have bit 0 to bit 7 actually explicitly represented. Bit 8 is there, but it is implicitly a 0. Okay, great. Cool. So this is all good, okay? But now the question is there any indication, which number is, whether the first number x is less than the second number y when we just perform a subtraction? Okay, so as it turns out, the overall borrow in a binary subtraction is all we need to determine whether the minuend, which is x, is less than the subtrahend, which is y. So now would be a good time to switch to Zernal, and we just have to go through a few examples. Okay, and let me go back to, that's not what I want. I want Zernal. I know it's here. There we go. Except you guys cannot see it, and neither can I. Zernal, where is it? There we go. Just have to move it into the window that you guys can see, because I changed the layout of the computer a little bit. Alright, so Martin is asking, what does the definition of T mean? Yeah, it's take away from a subtraction. Yep. It's basically the same thing as a borrow, but I don't want to use b because b is already the name of a function, and that would be very kind of more confusing. So that's why I use t to basically mean the borrow bit instead of the borrow function. Alright, so my tablet is not responding to my pen, so I just need to run the script again. Just hold on a second. And now it's working. Cool. Okay, so we'll go ahead and take a look. Oh, you're welcome, Martin. Okay, so what we'll do now is to go through a few examples to look at how we compare bit patterns. Okay, and we want to interpret the bit patterns into their unsigned values. Okay, so we want to look at, so let's say that we're dealing with 4-bit numbers. Okay, 4-bit numbers. In other words, in the terms that we have already introduced, m equals to 4, so bit 0 to bit 3 are the ones explicitly represented in this case. So, and these are unsigned. So we want to take a few kind of extreme cases. Okay, we want to look at 0 and make sure it's less than 1. We want to make sure that 1 is not less than 0. Okay, this is true. This is false. We also want to look at the more extreme cases, like what about the maximum value that 4 bits can represent? So from the lecture yesterday, we know the range of values that an unsigned integer can represent, given the number of bits. So since there are 4 bits, 15 is the largest value that we can represent. So we want to make sure that 15 is considered greater than 0, and 15 is less than 0 is false. And some people may look at this and go like, wow, that doesn't seem to be making any sense. Why, if we already confirmed that 0 is less than 1, why do we need to confirm that 15 is less than 1? Okay, it will be obvious later on why that is the case. So we want to look at the 4-bit subtraction, 0, 0, 0, 0, minus 0, 0, 0, 1, and 0 minus 1 is a 1, 0 minus 0 is a 0, 0, 0, and then there's an implicit 0 over here. 1 minus 0 is a 0. 0 minus 1 has a borrow of 1, and then 0 minus 1 is a 1 with a borrow of 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow of 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow of 1. Okay, so that is how we do binary subtraction. And we actually do not need to know about this part here. Okay, we don't need to know at all. All we need is to look at the overall borrow. If the overall borrow is a 1, then we can conclusively say that x, which is the middle end, is less than y. Okay, so that seems to work in this case. 0, 0, 0, 1 minus 0, 0, 0 is 0, 0, 0, 1. And I'm pretty sure we don't need to go through the borrow row because all the borrows are going to be zeros, right? So it has an overall borrow of 0 over here. But that tells us that 1 is less than 0 is false. Okay, so the borrow bit is a 1 if and only if x is less than y. So let me state it here. B is 1 if and only if x is less than y, or the value represented by bit pattern x is the value represented by the bit pattern y. Okay, that is the more precise way to say it, but we can kind of make it shorter and just say that x is less than y. So we're still doing okay so far. Okay, looks like there are no questions. All right, so next we'll move on, and this time we'll compare 0 to 15. 15 is represented by 1, 1, 1, 1 in base 2. 0 minus 1 is a 1 with a borrow of 1. 1 minus 0 is a 1. 0 minus 1, once again, is a 1 with a borrow of 1. 1 minus 1 is a 0. 0 minus 1 is 1 with a borrow of 1. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow of 1. 1 minus 1 is a 0. Okay, well, we don't care about the actual difference, and we just look at the borrow bit, which is a 1. So that means x, which is 0, is in fact less than y. Okay, that's a really kind of interesting conclusion because we already know way ahead of time that 0 is less than 15. And then we flip it around and we have 1, 1, 1, 1, which is 15, compared to 0. This is x, this is y. And we can see that it's just 1, 1, 1, 1 itself with a borrow of 0. So this is telling us that x is not less than y. X, which is representing 15, is not less than Y, which is representing 0. That seems to make sense. So are we good at this point? Is everybody convinced that the borrow bit alone can indicate whether the value of X, which is the minuend, is less than the value of Y, which is the subtrahend? So are we kind of convinced about that? David is typing. All right, all good. Excellent. So let me go back to the discussion here. So this portion over here, okay, this portion over here, okay, including this statement. So TM, T subscript M, is the overall borrow, because this is the one borrow that does not contribute to the difference, because it is out, because we don't have enough bits to include this in the difference. So this is the overall borrow, which is represented by this circled 1 over here, this circled 0, this circled 1, and also this circled 0 over here. All right, so this part here, when we look at everything from here, which is the conclusion, it is a statement, it is a theorem, and all the way down here is a very informal proof that this mechanism works. In other words, because of this proof, we know for sure that we can rely on the borrow bit alone to determine whether X, the minuend, is less than Y, the subtrahend. If B is a 0, X is less than Y is false. If B is 1, X is less than Y is true. Okay, so that's pretty easy. So now we move on to signed representation. So when we deal with signed representation, the first thing I want to kind of present here is another way to look at signed representation compared to the signed representation module. This is yet another way to look at it. V of X is the value of X. X is a bit pattern. Remember, X is just a sequence of zeros and ones. It does not have an inherent value associated with it. So in this discussion in section 4, V of X is saying, okay, let's look at not the bit pattern X, but let's look at the value represented by the bit pattern of X. Okay, what is it? What is the value represented by X? So if you want to ignore all of these derivations, it's okay. Okay, it is actually okay to ignore all the sigma notations, except for people who want to really understand why we can come to this conclusion. Then you might want to go through the derivation just to get a better understanding. But the conclusion is, okay, when you look at X as a bit pattern and V of X being the signed value represented by X as a bit pattern, it is like this. Okay, it is the summation of xi times 2 to the power of I. We have seen this before when we deal with base conversion, but when you look at the sigma, it only goes from digit 0 to digit m minus 2. In other words, the most significant bit, being bit m minus 1, is not in this sigma. Instead, it is outside, and it is being subtracted from the sigma. Okay, so how does that work? So what we want to do is look at an example. Okay, so let's go to Zernal and look at an example. So we'll look at an example that we have seen already, some of these bit patterns. Okay, so we want to look at 0, 0, 0, 1. Okay, and we want to find out the signed value represented by this. So it is going to be 1 times 1 plus 0 times 2 plus 0 times 4, because this is the sigma portion, minus 0 times 8 in this case. So this whole thing, now yes, I understand this is really kind of stupid, because you can see, oh, this is 0, this is 0, and this is also 0, so we just end up with a 1 here. So the value represented by 0, 0, 0, 1 as a bit pattern is just 1. Wow, woohoo! Okay, not surprising here. Now let's look at something that may be a little bit more interesting. Let's look at 1, 1, 1, 1. Okay, so 1, 1, 1, 1 as a bit pattern. is going to have the sigma is going to give us 1 times 1 plus 1 times 2 plus 1 times 4, because this corresponds to this bit here, this corresponds to this bit here, and this corresponds to this bit over here. So what is not included in here is the most significant bit here, but that is supposed to be subtracted away from the sigma. So this one here is telling us that we have a 1 times 8 to subtract away from the sigma. The sigma itself is going to give us a value of 7, and then what is outside is going to give us a value of 8. 7 minus 8 is -1. So this tells us that the bit pattern of 1111 as a 4-bit number is going to represent the value of -1. So do we have any questions about this example, which is illustrating, the result of this equation here? So are we all good here too? And let me flip back to the journal, so this way we can see the example. I'm gonna pause a little bit here until people either confirm that we are good or tell me that no, we are not getting a particular point here. Okay, kind of makes sense. Okay. Okay, so Catherine has a good question. 1111 can also represent 15, but remember the question. Remember what I said about what is the value of 1111, and my answer to that was, why do we care? Okay, so for the most part we do not care. When we add and we subtract, we actually do not care. It works in both cases. The carry look ahead mechanism will add correctly whether the value, whether it is a signed or unsigned interpretation. The way we do the carry look ahead subtraction is also going to work whether it is signed or unsigned. So the only time it makes any difference is when we have to deal with comparison. Okay, so in the context of section 4, which is where we are at this point, is we're only concerned about the signed interpretation of a bit pattern. We do not concern about the unsigned interpretation because that was already handled by section 3. Okay, all right, so now we move on. This module is not very long, but it is actually kind of confusing at certain times. So now we want to look at comparison. Okay, so in this case, x and y are actually talking about the value represented by the bit pattern x in a signed interpretation, and also the signed interpretation of y as a bit pattern. So instead of using v of x versus v of y, I just make it kind of simpler by saying x and y. So when we look at this, just as in algebra, it makes sense, right? It makes perfect sense. X is less than y if and only if x minus y is less than y minus y. Because if x is less than y, if I take away both the same amount from both sides of the comparison, then it would still be less than, right? The left hand side would still be less than the right hand side. But then, the right hand side, which is y minus y, becomes 0 because it cancels out. So that means if x is less than y, then x minus y is going to be negative. Does that make sense to everybody? This has nothing to do with computer science. This is just algebra. So are we good with this? Are we good with this part here? X can be a signed value, it can be positive or negative. Y can be a signed value, positive or negative. This is universally true. Okay, so if that is the case, it seems like we can just look at the sign bit of the difference, okay, to determine whether x is less than y or not. So what is the sign bit? So the sign bit here, okay, this is the definition of the sign bit. So the sign bit is bit m minus 1 of the difference. Now, is that really surprising that we call it the sign bit? No, not really. Because if you look at the sign bit, this is the sign bit, okay? Because it is bit m minus 1. So the most significant bit of a bit pattern, when you want to look at the bit pattern as in the signed interpretation, that bit, the most significant bit, which is also the leftmost bit of the bit pattern, is known as the sign bit. Because if that bit is a 1, the whole value is going to go negative. Because we know from the theorem earlier that this power of 2 alone is greater than the summation of all of those powers where I goes from 0 to m minus 2. So this is also another reason why that theorem is important, because if x subscript m minus 1 is a 1, I don't care what the other bits are. I know the value being represented is negative. And that is also why bit m minus 1, where m is the number of bits in the bit pattern, is known as the sign bit. It is also known as the most significant bit, but when we are looking at it from the signed perspective, we normally would call it the sign bit, but they are actually equivalent. So do we have any questions about the name sign bit versus the name most significant bit, and why it alone can determine the sign of a value? So I'm going to pause a little bit here because there's a little bit of digesting involved, and if there are any questions, now would be a good time to ask. All right, so looks like there are no questions. Now when I say something like that, okay, Martin is typing. So when I say something like that, okay, looks like there are no questions, and you guys want to have more time to think about it, just type in Discord to say that I need more time. Okay, that's no problem. If you don't want the whole class to know that you need more time, because you don't want the whole class to know about it, you can just direct message me. But don't feel embarrassed, because if you feel that you need more time, chances are the rest of the class probably needs more time too. So it's no problem to ask for more time. So Martin is asking, can I explain that a little bit more? Okay, so maybe an example will help. Okay, so let's take a look at some examples, and looking at the next page over here. So we'll take a look at -2. Okay, so I want to represent -2 as a 4-bit number. So we know that the format of the bit pattern is going to be something like this. Let's call this x. Okay, so we know that x0 times 1 plus x1 times 2 plus x2 times 4 minus x3 times 8, we want this to equal to -2. Is that okay? This is a direct result of expanding the sigma notation over here. So are we getting this part? And v of x in this case is -2, because that's the value that we want to represent. So we're good. Okay, Richard says it's good. What about the rest of the class? Does anyone need more time? Okay, I'll put it that way. Good so far. Okay, and good. Okay, thank you for the confirmation. So now we just have to figure out all the bits, right? Remember x0, x1, x2, and x3, they can only be zeros and ones. They cannot be anything else. Okay, they can only be zeros and ones. So the first thing we know is the overall value has to be a -2, And the only way to make this happen, because there's only one subtraction, right, to turn everything negative, which is this term here. So we know x3 has to be a 1. Okay, so we know this has to be a 1. So there's a -8 and then plus something over here that will give us a value of -2. So that means all of these, they have to add up to what? 6, right? Because 6 minus 8 is -2. So when you say that, okay, all of these need to add up to 6, then by base conversion, okay, this boils down to basic base conversion now. So we know this is a 1, we know this is a 1, and this is a 0. So what this is telling us is the bit pattern to represent -2 is 1, which is x3, 1, which is this x2, 1, which is this x1, and a 0. Okay, so this is going to look really ugly if I want to. Okay, I'll put it this way. I'm going to reuse the concept of a tunnel, right? Why not? So reusing the concept of a tunnel, this is the bit pattern to represent -2. Is that okay? It has to be a 0 because if x2 is a 1, it takes care of the 4 in the 6. So we only have a 2 remaining. So x1 has to be 1 to take care of the 2. Yep, there we go. So it's basically converting 6 into the base 2 representation using 3 bits. All right. So does that address the concern earlier? Of why x3 in this case is called the sign bit, because x3 alone will determine the sign of the value, whether it is negative or not. So are we good here, or do we need more time? Okay, excellent. Thank you. So now we move on, and we'll use some examples. Okay, so we'll use a few examples to illustrate how this works really well, and then we'll use a few examples to show why this is not working. Okay. Okay, why is it not working? So we'll look at 0 versus 1. Okay, so we'll do the same thing as before: 0, 0, 0, 0, minus 1, 1, 1, 1. And this time I'm just going to do it. Oops, sorry, my bad. I said, it should be 0, 0, 0, 1. There we go. Okay, so this time we're going to do the subtraction really fast because it's really exactly the same subtraction as last time, but we pay attention to something that is different from last time. Okay, 0 minus 1 is 1 with a borrow. Okay. Okay, so you can see that the way we perform the binary subtraction is exactly the same as last time, except last time we looked at the overall borrow, which is here, but this time we look at the most significant bit of the difference, which is a 1. Okay, that makes sense, right? X is less than y if and only if d is less than 0, because after all d is the difference, which is x minus y. Okay, so it seems to make sense. Let's look at another example. 0, 0, 0, 1 minus 0, 0, 0 is 0, 0, 0, 1 with an overall borrow of 0. So, but once again, we do not pay attention to the overall borrow anymore because we just need to look at the sign bit of the difference, which is this one here. Okay, so this is telling us that d is less than 0 is false, and that can only be the case when x is less than y is also false. Okay, seems to make sense. Okay, fine, we're good. Now, if you think we are not good, just let me know. Okay, I'm just saying that we are good because this seems to make sense. Now let's try something else. Let's try this. Okay, minus 1, 1, 1, 1. Okay, And basically redoing the same math as last time. 0 minus 1 is a 1 with the power of 1. 1 minus 0 is a 1. Okay, so it's basically the same mechanism as last time. So this time we look at the sign bit of the difference, which is this one here, and we say, does that make sense? Well, the answer is it makes perfect sense, because 0, 0, 0, 0 is representing the value of 0. 1, 1, 1, 1 is representing the value of negative 1. 0 is negative 1 is false. But that's also why the sign bit of the difference is a 0, because we are saying that d is less than 0 is false, x is less than y is false. Is that working for you guys? Can everybody see how even though 1, 1, 1, 1 now is representing a different value, but we can still use binary subtraction to help us know which of x, y is whether x is less than y. But this time we just pay attention to the sign bit of the difference instead of the overall borrow bit. Okay, I got a few people typing. Richard says okay, and I thought Catherine was typing too, so I'll wait for that too. Okay, all right. So the key here is this particular bit. If this bit is a 1, it means the difference is negative. And if this bit is not a 1, if it is a 0, it means the difference is not negative. And then everything kind of boils down to, let me scroll to the right portion here. So everything boils down to this part, okay? Because x minus y is d, that's our difference. So if d is negative, then the sign bit of d, which is the most significant bit, which is the bit that I point out in all the examples, that is going to be a 1. If that bit is a 0, that means d is less than 0 is false, which then will let us deduce that x is less than y is also false. Okay, all right. So it might take a little bit of time to actually understand the math behind it, but at this point we just make the claim that the sign bit of the difference is what is the indicator of whether x is less than y. The minuend is less than the subtrahend in the subtraction. But then we'll start to look at examples that do not work. Okay, so we'll now go to some examples that goes like, that doesn't seem to work, and we'll explain why why those examples are not working. So with 4 bits as signed numbers, okay, 4-bit signed, the range goes from -8 to +7. Those are the values that we can represent using only 4 bits. Okay, and the method to compute the range of values is already discussed when we talked about signed representation. So we are just kind of reusing that applied to 4 bits to determine that the range is from -8 to +7. So it would seem to be perfectly okay to compare 8 and 1, right? Okay, so 8 is within the range, 1 is within the range. We should be able to determine that -8 is less than 1. So let's go ahead and figure out whether that works or not. So -8, okay, so let's first find out what is the binary representation, the binary 4-bit representation of -8. So we got x0 times 1 plus x1 times 2 plus x2 times 4. This is a 1 over here. And then subtract from that x3 times 8. And I want this to be exactly -8. Can someone quickly point out the values of x0 to x3? Each one can only be a 0 or 1. All zeros for x0, x1, and x2. What about x3? This guy needs to be a 1, doesn't it? Yes. So the other ones are all zeros, like so. So that means 1, 0, 0, 0 is representing -8 in base 2 with a 4-bit number. Signed representation. Are we good? All right. I'm assuming we are good here. Okay. So, assuming we are good. Okay, good. Thank you. Thank you for the confirmation. So, assuming we're good here, now we can safely say, okay, let's do the subtraction here. I want to confirm that -8 is less than 1. This is -8. This is 1. Do the subtraction. Okay, 0 minus 1 is a 1 with a borrow of 1. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow of 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow of 1. 1 minus 0 is a 1. 1 minus 1 is a 0, and neither has a borrow. So this is the subtraction, the binary subtraction. So remember, we only look at the sign bit of the difference, okay, which is a 0 this time. Whoa, hold on a second here. This is telling us that d is less than 0 is false, which can only happen if and only if x is less than x minus y is not less than 0, which can then only happen if x is less than y is false. What is going on here? Because x is representing -8 and y is representing 1, so this doesn't seem to be working. This is not good. Okay, so can anyone remember why this kind of math does not work? You have a number wheel, right? -8 is over here, and this line is representing this line is representing the negative side versus the non-negative side of the number wheel. This -8 turns out to be the last value that is negative. So if you subtract 1 from it, then it becomes the most positive value, which is 7. That is why we got 7 as the answer, because we ran out of digits to represent the result of the subtraction. Is that okay? Does everybody now understand why the sign bit of the difference in this case does not tell us correctly whether the minuend is less than the subtrahend? All right, excellent. So now we move on, and let's see, we want to make a new page. Okay, so we now move on, and we now say, so when we run out of digits to represent the result, then we cannot trust the sign. So now the question is, can it go the other way? In other words, can we end up with the sign bit being a 1, but it is actually erroneous, and the actual result should be not less than, but the sign bit is telling us that it is less than, okay? And the answer is, yep, that can happen as well, okay? So let's see what we need to do to make that happen. So we want to compare 7 to -1, okay? 7 is less than -1 is supposed to be false, okay? All right. So now we want to look at the representation of 7. 7 is represented by 0, 1, 1, 1 in base 2. -1 is represented by 1, 1, 1, 1 in base 2. So now we can carry out the binary subtraction. 0, 1, 1, 1 minus 1, 0, 0, 0. Okay? So we just go through the usual binary subtraction mechanism. 1 minus 0 is a whoops, is a 1. 1 minus 0 is a 1, and neither has a borrow of 1. 1 minus 0 is a 1. 1 minus 0 is a 1. We don't have a borrow of 1. 1 minus 0 is a 1. 1 minus 0 is a 1 with no borrow of 1. And then 0 minus 1 is a 1 with a borrow of 1. 1 minus 0 is a 1 again. Okay, so right, okay, my bad. My bad. Okay, sorry. 0 1 1 1 minus 1 1 1 1. I put it over here and then I just my brain fart. Thank you. So let's redo this. 1 minus 1 is a 0. 0 minus 1 is 0. We don't have a borrow of 1. 1 minus 1 is a 0. 0 minus 0 is a 0 with no borrow of 1. 1 minus 1 is a 0. 0 minus 0 is a 0 with no borrow of 1. 0 minus 1 is a 1. 1 minus 0 is a 1. But this 0 minus 1 gives us a borrow of 1 over here. Okay, there we go. Much better. Thank you. Okay, so now we look at this result. The other one works too. Okay, the other one is comparing 7 to -8, but it's not the example that I want to use. So when you look at this sign bit here, the sign bit says d is less than 0. Okay, so that can only happen if and only if x minus y is less than 0, because d is x minus y. And that can only happen if and only if x is less than y. But it doesn't make sense, because this is x, this is y. The value of x is 7, the value of y is -1. So 7 is less than -1 is false. This is the other case of overflowing, because what happens in this case is when you look at the number wheel, this is 0, this is -8, and this line divides which half is negative and which half is non-negative. Okay, so what we have in this case is we have a 7 here, but to subtract 1 from 7, to subtract -1 from 7 is to add 1 to 7. So we went in this direction. We went from 7 to the -8 because we ran out of bits to represent the actual answer of +8. Okay, so in both cases, so this doesn't work either. So in both cases, we notice something about the sign bit. I'm looking at the time here. We got 10 minutes. We're definitely going to cover everything for the lab. So we are looking at the sign here. Okay, so this is x, which is called the mean u-end, and this is y, which is called the subtrahend. I'm putting these terms out because you need, because the lab for today is going to refer to these terms, so that's why I put these terms out. And we have some bits over here, but I only want to look at the most significant bit this time. Okay, so that's the most significant bit, and this is squiggly because I don't really care about these bits. Okay, squiggly over here. This is a subtraction. And for the most part, I don't really care about the Q or the T row in this case. T row has one more thing over here. And then when we come to the D row, we only care about the most significant bit over here. And I don't care about the squiggly line here. In other words, when you compare, you have to perform the actual binary subtraction. But after the subtraction, we only want to look at these 3 bits. So let me highlight the 3 bits that we want to look at. This is 1, this is 1, and this is 1. Okay, so the notation of these 3 bits, referring back to the notes, okay, because I do want you guys to understand the terminology that I used in this case. So the notes is using x, y, and d, and they're all bit m-1, but in the lab they're referred to something that is slightly different. But I do want to show basically show you where we are at this point. Okay, so that's just the notation. Okay, so that's just the notation, and So this bit over here is x subscript m minus 1. This bit here is y subscript m minus 1. And this bit over here is d subscript m minus 1. So I'm now saying that looking at these bits, I can now determine whether x is less than y. Really? Even when sometimes we have overflow, we can still do that? Well, the answer is yes. Okay. So what we want to do is to say when there's no overflow, okay? When there is no overflow, we can trust d subscript m minus 1 to indicate whether the value of x is less than the value of y. Okay, we kind of showed that already. So the only time when we cannot trust dm minus 1 is when there is an overflow situation. So now we want to know when there's an overflow situation. Okay, so now we need to know when there's an overflow. There's an overflow when the sign of d does not, okay, in quotes, does not make sense. Okay, so what do I mean by does not make sense? Let's look at all the combinations. Okay, this is x m minus 1, which is the sign of x, y m minus 1, which is the sign of y, d m minus 1, which is the sign of the difference. And now we ask, does this make sense? Okay, so we have a truth table. This time we got 8 entries: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so now we look at each row and we ask, just looking at the sign bits of x, y, and the difference, does it make sense? Can it happen? So the first one says x is not negative, y is not negative, and the difference is not negative. Can that happen? Sure. 3 minus 2 is 1, and they are all non-negative. Okay, so does it make sense? Yes. Let's look at the second row. X is not negative, y is not negative, but the difference is negative. Can that happen? Yep, that can happen. 1 minus 2 is negative 1, so it can certainly happen. All right, so we say, yep, that makes sense. We look at the third row. Can that happen? X is non-negative, y is negative, and the difference is non-negative. Can that happen? Makes perfect sense, right? Because remember, y is negative and is being subtracted from x. So it's really basically saying, adding the absolute value of y to x, which is already non-negative to begin with. So the difference being non-negative seems to make sense. Okay. Now we have this case where x is non-negative, y is negative, and the difference is negative. So this is saying that if I subtract a negative quantity from a non-negative quantity, we end up with a negative quantity. Does that make sense? Okay. We actually have encountered this case already. It does not make sense. Okay, we actually encountered this case already when we asked what is 7 minus 1, and the end result is what? 7 minus 1 turned out to be negative 8. So it doesn't make sense. So we will put a cross here. This row here says, x is negative and y is non-negative. We are subtracting a non-negative quantity from a negative quantity, and we end up with a non-negative quantity. Does that make sense? It does not make sense, right? And we have encountered this case already as well, because we had, what was it? Was it -8 versus 1? Yeah, it was -8 minus 1 being 7. It does not make sense. So we'll put a cross here. So now, I'm just going to skip a little bit forward. This one actually makes sense, this one makes sense, and this one also makes sense. So when we have the rows corresponding to something that does not make sense, then when we flip the question around and ask, do we have an overflow? No, 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 yes, yes, no, no, and no. Is that okay? Does everybody see how we can determine whether a subtraction ends up in an overflow situation? How we can only look at the sign bits to determine that there is or there's not an overflow situation. And if I were to highlight the overflow situation, it's, oops, I should have used a highlighter. This row and this row are the only two rows that indicate that there is an overflow situation. Are we okay so far? All right, cool. So now the question is, if I were to define overflow as a bit, okay? Okay, this is the wrong color. So if I were to define overflow as a bit, okay, which is uppercase O, how would I define it? Well, in the first scenario, which is this row over here, I can say that if I negate xm minus 1 and ym minus 1 and dm minus 1, if this conjunction is a 1, that means it has an overflow, because when this expression is a 1, it tells me that xm minus 1 is a 0, ym minus 1 is a 1, and dm minus 1 is a 1. That's the only time when this expression, the conjunction, is going to be a 1. Okay? But wait, there's one more scenario where we can end up with an overflow, which is the next row over here. So if I want to have a conjunction that is true if and only if xm minus 1 is a 1, ym minus 1 is a 0, and dm minus 1 is a 0, then I end up with something like this. I end up with xm minus 1 and the negation of ym minus 1 and the negation of dm minus 1. So this particular conjunction is true if and only if we have this scenario happening. So if I were to use color highlighting, okay, the green part corresponds to this, the orange part is corresponding to this. And these are the only two rows, these are the only two scenarios where we have an overflow. And we are out of time, but I still want to kind of finish this discussion. So the discussion, the conclusion now is, when do we know x is less than y? So the conclusion is x is less than y, or the value of the bit pattern x is less than the value of the bit pattern y, if and only if dm minus 1, okay, because that's one factor, but we know that this cannot be trusted, okay, not all the time, exclusive or with big O, the the overflow bit. So let's take a look at this one last bit here, okay, and ask, why is it like this? So when we look at this, and this is also known as L, the L flag. So we look at dm minus 1, we look at the overflow, and we look at the question of whether x is supposed to be less than the value of y. So there are four scenarios that can happen: 0, 0, 0, 1, 1, 0, and 1, 1. So we look at these four scenarios. on the first row, we have dm minus 1, which is the sign bit of the difference being a 0, and there's no overflow situation. So that means the difference is computed correctly. It is actually non-negative. If the difference is non-negative, then x, the value of x is less than the value of y, is also false, because in this case we can trust the sign bit of the difference to conclude whether x is less than y. On the second row, we have the sign bit of the difference being a 0, but the overflow flag is a 1. So when the overflow flag is a 1, it's basically telling us don't believe the sign bit of the difference. Okay? So in this particular scenario, the sign bit is actually quote unquote supposed to be a 1, but because of the overflow situation, it registers incorrectly as a 0. So in this case, the value of x being less than the value of y is actually true, because the 0 is actually misreported. On the third row, the sign bit is actually correct because there's no overflow, but if the sign bit of the difference is a 1, it means the difference is negative, which also means x is less than y. So this is also a 1 over here. And then on the last row, the difference is negative according to the binary subtraction, but the overflow says don't trust it because it is wrong, because we have an overflow situation. So the sign bit is supposed to be 0, but it registered as a 1 because we ran out of bits. So in this particular scenario, the actual sign bit is supposed to be a 0, which means the difference is not negative, which also means the value of x is less than the value of y should be false. Okay, and the L flag is basically just that. The L flag is the exclusive OR between the sign flag of the difference and the overflow flag. So this is the very last bit, but this is also the conclusion of the entire chapter, because of the entire module. Because when we go back to the module and scroll down here, it is basically saying, the L flag is the exclusive OR between the S, which is the notation of S being the sign bit is automatically referring to the sign bit of the difference. So when we look at S as a flag on its own, it is referring to the sign of the difference, and that definition is established up here. All right, so we actually managed barely to finish the entire module. So now you have everything that you need to get started with the lab today. And the lab today is set up already. I just need to go back and figure out the passcode. And it's subtraction and compare. That's the lab for today. And the passcode is it's either my computer or Canvas is extremely slow. Are you guys experiencing the same thing? Okay. Alright, so the flags is the passcode. I will put it into Canvas here. There we go. And I will pin it. And there we have it. Okay, this is the end of today's lecture. If you do have questions about the concepts, or if you have questions about what the question or what the lab is asking, I will be on the text channel after this. So I'm gonna close the live session at this point, and also close the YouTube streaming. But I'll be paying attention to